Have you ever really thought about light? I mean, why your shadow perfectly copies you, or how the moon seems to just glow up there in the night sky? Well, today we're going to pull back the curtain on the light that's all around us, from simple shadows to wild reflections. All right, let's get into it.
So, our story starts with this curious kid named Keshav. Picture this. He's on a bus at night, looking out the window at this moonlit world. He sees fireflies blinking on and off, car headlights cutting through the dark, and of course, that big, bright moon. And all of this gets him thinking, sparking a question that's really at the heart of everything we're talking about today.
And this is the question. Is the moon basically a giant light bulb in the sky? Or is it more like a massive mirror, just bouncing light from somewhere else? It's a simple question, right? But the answer is what kicks off our whole journey into understanding how light works.
Okay, so to answer Keshav's question, we have to make a really important distinction. We need to figure out the difference between things that make their own light and things that just, well, borrow it.
And it all comes down to this: luminous versus non-luminous objects. Luminous objects are the light makers. Think about the sun, a candle flame, even those fireflies Keshav was watching. They all produce their own light. But non-luminous objects, like a chair, a book, or, you guessed it, the moon, we only see them because they're reflecting light from a luminous source. So the answer to Keshav's big question? Nope. The moon doesn't make its own light. That beautiful moonlight is just sunlight bouncing off its surface.
And you know, our own quest to make light is a pretty amazing story. It goes way back, from the first time we learned to control fire, all the way to the invention of electric lamps that totally changed the world. And now we're all about super efficient LEDs, trying to save energy. It's a journey that's still going on.
So we know where light comes from, but how does it actually move? How does it get from the source to our eyes? Well, the answer is, believe it or not, a straight one. Think back to those headlight beams Keshav saw. I mean, they look like perfectly straight lines, don't they? But this is science, and we can't just go by looks. We need some proof. So how can we be absolutely sure that light travels in a straight line? Turns out a couple of super simple experiments can show us exactly how. All right, check this out. Imagine you line up 3 matchboxes, and each one has a little hole punched right in the middle. If you shine a flashlight through the first hole, and they're all perfectly lined up, the light zips straight through all 3 and hits a screen at the end. But, and this is the important part, the second you nudge one of those boxes out of line, poof, the light is blocked. It can't bend around it. It's such a simple way to see that light travels in a straight path. And here's another way to think about it that makes it even clearer. If you look at a candle flame through a straight pipe, no problem. You see it perfectly. But the moment you bend that pipe, the flame is gone. You can't see it anymore. It's just more proof that light needs a direct, straight shot to get to your eye. Okay, so we've established it. Light travels in a straight line. So what happens when something gets in its way? This simple idea takes us into the familiar and kind of cool world of shadows. To really get shadows, first you have to think about what's blocking the lights. We can basically sort materials into 3 groups. You've got transparent stuff, like glass, that lets pretty much all the light pass right through. Then there's translucent stuff, like tracing paper, which lets some light through, but it gets all scattered. And finally, you have opaque materials, like cardboard, that block light completely. And that's exactly what a shadow is. It's that dark spot behind an opaque object where the light just can't get to. Since light travels in straight lines and can't go through the object, it leaves a dark patch on the other side. A shadow is literally just an absence of light. What's really fun is that you can totally control shadows. The rules are simple. Move something closer to the light, its shadow gets bigger. Move it closer to the wall, the shadow gets smaller. You can even tilt the object and watch the shadow's shape get all distorted. But notice the one thing you can't change? The shadow's color. It doesn't matter if your object is bright red or blue, the shadow is always just dark. And this whole idea of playing with light and dark isn't just science, it's art. For centuries, people all over the world have used these exact ideas to create the magic of shadow puppetry. In places like Andhra Pradesh, they have a form called Tolu Bamalata, where puppeteers tell these incredible stories with using nothing but a light, a screen, and some carefully cut out figures. It just goes to show you, sometimes the best stories are told with darkness. So we know light can be blocked to make shadows. But what happens when it hits something smooth and shiny, like a mirror? It doesn't get blocked. It bounces. And this is what we call reflection. Yeah, reflection is just light changing direction when it hits a surface. You can see this yourself. Just take a mirror outside on a sunny day. You can aim that beam of sunlight wherever you want. You're literally changing the light's straight path and sending it off in a totally new direction.
Now, the image you see in a regular flat mirror, what scientists call a plane mirror, follows some very specific rules. It's always upright, it's always the same size as the real thing, and it looks like it's just as far behind the mirror as you are in front of it. But there's one really weird thing it does that you've definitely noticed. It's called lateral inversion.
Ever wonder why the word ambulance is written backwards on the front of the vehicle? Well, that's lateral inversion in action. The mirror in the car in front flips the image so the driver sees the word the right way around in the rearview mirror and knows to get out of the way. It's actually a pretty brilliant life-saving trick using a basic principle of light.
All right, now we're going to take everything we've learned so far, that light travels in straight lines and can be blocked, and use it to understand a really amazing little device, the pinhole camera. The design couldn't be simpler, really. It's just two boxes, one sliding inside the other. You poke a tiny hole, the pinhole, in the outer box and put a translucent screen on the inner box. Then you just point the pinhole at something bright, like a tree on a sunny day, and an image actually forms on that screen inside. But what you see might just surprise you. The image is upside down. So why does that happen? Well, it all goes back to that first rule. Light travels in straight lines. The rays of light from the top of the tree go in a straight line through the pinhole and hit the bottom of the screen. And the rays from the bottom of the tree travel in a straight line and hit the top of the screen. This super simple device, which is basically the granddaddy of every camera ever, gives you this incredible visual proof of how light works.
And that leaves us with one final kind of mind-blowing thought. If one tiny pinhole can capture an entire upside-down world, and one little piece of a mirror can reflect a whole giant tree, what does that say about how we see the world every single day? It means the light hitting your eyes right now is carrying an unbelievable amount of information about everything around you. So next time you see a reflection or make a shadow puppet, just remember the incredible straight line journey that light took to make that moment happen.